Hello, Andre. Hi, Steven. Hello, Sinmiro. Hello, everybody. Thank you so much for being here. Can we get 10 likes? Can we? So which is real or imaginary time? It is simply a matter of which is the more useful description. One can also use the sum over histories along with the no boundary proposal to find which properties of the universe are likely to occur together. For example, one can calculate the probability that the universe is expanding at nearly the same rate in all different directions at a time when the density of the universe has its present value. In the simplified models that have been examined so far, this probability turns out to be high. That is, the proposed no boundary condition leads to the prediction that it is extremely probable that the present rate of expansion of the universe is almost the same in each direction. This is consistent with the observations of the microwave background radiation, which show that it has almost exactly the same intensity in any direction. So, as we know, the cosmic microwave background radiation temperature has been measured for almost, I believe it's been a while, like a couple of decades worth of measurements and whatnot, and we keep finding that it's about the same average temperature no matter which direction you do this measurement in and which direction you look, pretty much. If the universe were expanding faster in some directions than in others, the intensity of the radiation in those directions would be reduced by an additional redshift. So if the universe had an expansion which was different in a certain direction, for example, faster in a particular direction than some other particular direction, then we would see a difference in the CMB temperature in that direction, okay? It would, the intensity of the radiation in those directions would be reduced by an additional redshift because that part of the universe has receded more, is accelerating away more than other parts of the universe, if this were to happen. Further predictions of the no boundary condition are currently being worked out. So this whole like boundary thing, like, is there really a boundary? Or is the universe kind of flat, infinite, and sort of expanding in every direction in sort of the same way, you know? So a particularly interesting problem is the size of the small departures from uniform density in the early universe that caused the formation first of the galaxies, then of the stars, and finally of us. So that's the other thing, is that there are small perturbations to the smooth universe. These are called higher order perturbations of the smooth universe, or little overdensities in the smooth universe where things are not quite as uniform as when we say uniform, right? Not perfectly uniform. There are some higher order perturbations to the uniformness or the homogeneity. So, but those little perturbations away from totally smooth, basically roughness or overdensities, is how we got the galaxies and the stars and ultimately us, because of course we're part of the, this solar system comes from a gigantic gas cloud that condensated to make the sun and the planets and planetesimals and whatnot, and now we're here. But again, that gas cloud probably comes from the death of some star, and that star comes from another maybe previous star, and then galaxies. All this stuff is really a result of the inhomogeneity in the completely smooth but not really completely smooth universe. At a very large scale, the universe looks very uniform, very homogeneous, and very isotropic. But actually, there are these little overdensities which led to the formation of galaxies, stars, and ultimately us. So it's very important, these overdensities. The what caused those overdensities is also a very important topic that we'll get into. Hello, Andre. Hello, Haru. Hello, Mike D. Thank you. Present teacher, good. Roll number 21, good. Thank you for being here. Hello. Can we get 10 likes? New people? Late people? The ones who are late and coming into class just now. Can we get 20 likes? Can we get 10 likes?